So we can start recording? Mm-hmm. Okay. All right, well, welcome back to the fourth lecture of our Generalized Complex Geometry Learning Seminar. So today what I'd like to do is to talk about, or is to introduce the Courant bracket, and so that will be section 2 of today's lecture. I think our approach here to the Courant bracket is that it's going to be a kind of deficient, that the double of the tangent bundle, or the extended tangent bundle, is going to be a sort of deficient Lie algebroid, and that deficiency is going to be characterized in terms of the canonical bracket, or the canonical symmetric bilinear form on the fibers of the extended tangent bundle. So we'll see that. But first, we'll review Lie algebroids, and I think it would be good for us to maybe cover some of the material a little bit that we did see last time. Then we'll introduce the Courant bracket, and then following that, we'll abstract from all of the properties that we see of the Courant bracket and define from that the notion of a Courant algebroid. And so in this sense, a Courant algebroid is going to be a weaker, like a weaker version of a Lie algebroid. All right, so let's jump into it. First, I want to recall, so this lecture begins with a flashback. The first definition we saw in this entire course, namely that of a generalized material. So recall that a generalized complex structure on a smooth manifold M is a smooth assignment script J of orthogonal linear complex structures to each fiber of the extended tangent bundle. So this here is the extended tangent bundle of M. That is, at every point x of M, the extended tangent bundle is the direct sum of the tangent fiber at x and the cotangent fiber at x. Subject to the condition that the plus I eigenbundle of J is Courant integrable. So there's a little bit of, maybe there's a little bit of technicality here, because of course the plus I eigenbundle of J doesn't, it doesn't live on the extended tangent bundle, it's on the complexification. So this is going to be a in terms of complex Courant algebroids, but we can see that we're definitely moving in the direction of the core definitions. Okay, so that's sort of the motive. So this is kind of the motivation. So let's then start. So 1, Lie algebroids. So what I'd like to do here is to give the full definition of a Lie algebroid again, and to list some of the key examples. And today I'm only going to think about real Lie algebroids, because that's the material that we're going to be directly abstracting from when we think about Courant algebroids and the Courant bracket. So recall definition. A Lie algebroid on M consists of three pieces of data, three data. One, a real vector bundle L over M. Two, a Lie bracket a Lie bracket on the sections of L over M. And 3, an anchor map. Where an anchor map is a smooth bundle map A from L to the tangent bundle of M. So smooth bundle map. And then we had sort of a picture for this. So here's M, here's L over M. We take a point X, we have the fiber of L at X, and the anchor map A maps from that fiber Lx to the tangent fiber of M at X. And then we have some conditions on this. So, let me see. Actually, I'm going to erase this here. I'd like to keep the definition on one board. So such that we have two compatibility conditions. First, there's a Lie algebra homomorphism condition, which just says that the map on sections induced by the anchor map is a morphism or a homomorphism of Lie algebras. So A x y is equal to ax ay for all sections x and y of the algebroid. And then second, we have a Leibniz condition, which says that the Lie bracket of x and fy. So here f is it's a smooth function on M, is equal to f of xy, or f multiplied by xy plus ax times f, or this is ax is a vector field on M, and we're applying that vector field as a differential operator to the smooth function f, and we're multiplying that by the vector field y. So that's for all xy in sections of L, and for all smooth functions f. Oops. And then I'll just list the key examples. So first, we can take our Lie algebroid to be a Lie algebra mapping to a point. So in this case, the point is our manifold M, and the Lie algebra is the unique fiber of L. So in this case, we can set our anchor map to be 0. Or we must set the anchor map to be 0. The tangent bundle here is 0. Second, we can consider as a Lie algebroid the tangent bundle to M itself. In this setting, the anchor map is the identity, and the bracket, sorry, I should say that in the first example, we'll take the bracket to be the standard Lie bracket, or to be Lie bracket intrinsic to G. And in this setting, we'll take the Lie bracket on sections to be the standard Lie bracket on vector fields. Third, we have for any integrable distribution on M F. So let's see. This is not. Let's see. So F is a integrable subbundle of the tangent bundle, subset of Tm. In this case, the anchor map is the inclusion of F into the tangent bundle, and the Lie bracket on sections is simply the Lie bracket on vector fields. And this is this is well defined because we're assuming that F is an integrable distribution, which just means that its sections are closed under the standard Lie bracket. So maybe I'll just make a note of that, integrable distribution. And then fourth, and very interestingly, we have the Atiyah algebroid. And the data that the Atiyah algebroid takes is a principal bundle P. Let's say a G principal bundle P over a manifold M. We obtain a short exact sequence of vector bundles on M, not on P, but on M, given by, let's see, so short exact sequence 0 to the adjoint bundle of P. This is a vector bundle on M. To this is the Atiyah algebroid, to the tangent bundle 0. So we can think of the Atiyah algebroid as sort of like a fiber-wise extension of the tangent bundle to M by the adjoint bundle to P. And recall that we can think of the adjoint bundle as being sort of consisting of generic vertical tangent fibers to P. I'm gonna draw a picture. So here is P. This is in this image. This is drawn as an S1 principal bundle over M. Let's see. So here's X, the fiber of P at X, and tangent fiber to M at X. Then we can think of the fiber add P at X as sort of being any of these vertical tangent bundles. So the anchor map is obtained from this short exact sequence. It's this one. So we can think of the anchor map again in some sense as registering the horizontal component of an element of at P. So here at P we can think of as being a generic tangent fiber, not necessarily vertical tangent fiber, but a generic tangent fiber to a point on the fiber of X. So this includes then the horizontal directions. The anchor map then is given by projecting that tangent element, or generic tangent fiber element, down to the tangent space at X, and then the Lie bracket on sections of the Atiyah algebroid is simply inherited from the Lie bracket on S1, or sorry, the Lie bracket on G, the Lie bracket for G invariant vector fields on P. Okay.
So
yes.
Point fiber-wise, we have the direct sum, Txm plus xp equals, because you say it's a short exact sequence in terms of vector bundles.
Yeah.
So it's exact on, at the level of the
fibers.
Of the fibers.
I think so. Yeah.
Okay. And so, can you write the bracket quickly, or just sketchily?
I can say it, or okay, because I believe that sections of at P should be G invariant vector fields on P.
Yes.
We just take their bracket.
In TP, in the tangent bundle of P. Okay.
And that's going to be G invariant.
Right.
So in other words, it's going to give us a section of the Itia bundle, and that gives us our bracket.
I see.
Are there any questions? Yeah.
What's vector bundle in this situation? P isn't vector bundle.
P is not a vector bundle. No, but we have a vector bundle here. We have a vector bundle here. Let's see. So specifically, the vector bundle, or the okay, good question. At P, the fiber at X, let's say, is going to consist of G invariant vector fields restricted to the fiber PX. So they're not G invariant vector fields on the fiber. That would then be the adjoint bundle. They're G invariant. They're vector fields that can point off the fiber, but we still require them to be G invariant. We can still act on them by G. Does this? Okay. So for example, here, can I draw? Here is an element of at P. It's not an element of the adjoint bundle because it's pointing off the it's pointing off the fiber. If it were tangent to the fiber, then it would be an element of the adjoint bundle.
Okay. Is there some? It looks very abstract. Is there some intuition? Maybe there are real objects which can be perfectly described by algebroids.
You mean do algebroids have like a canonical home in mathematics where they're really needed and they naturally arise? So sort of.
Yes. Why we see on function from vector bundle to tangent.
So my honest answer is that I'm new to this material here, but my intuition, and actually Sylvan is he works with this material in his research, but my intuition, maybe Sylvan wants to say something about this, is that that we're really sort of we're thinking of the algebroid as like a quasi-tangent bundle. So we're associating the elements of the algebroid with elements of the tangent bundle, but we might associate two Lie algebroid elements with the same vector bundle element, with the same tangent vector, And on the other hand, we might not, or it might not be the case that for every tangent vector, there's a Lie algebroid element that is associated to it. So I'm thinking of it as like a distorted tangent bundle, where we can have multiple elements associated to the same direction and magnitude. But again, so I am also being introduced to this material. Sylvan, do you have?
As an example, natural example, I think is arise from gauge theories, where you have in gauge theories you have a symmetry which is local, which varies over space-time, which depends on the point, obviously. You have, so it's a section into a Lie algebra. It's a function from the manifold into a Lie algebra that acts on the fields, and this can be seen, if I'm correct, as a from the manifold to a Lie algebra. You can encode the theory as a section of a Lie algebroid. And the anchor map is the projection to the vector field that acts on the physical field, I think.
I see. This sounds very, very, very evocative of this kind of example. I mean, so I think sometimes and I don't really look at physics stuff that much, but in physics, sometimes when we have a map from the base manifold to a Lie algebra, that's like a concrete or a local version of a map, or sorry, of a section of the adjoint bundle. If the principal bundle is trivialized, then we can canonically identify by that trivialization the adjoint bundle with the Lie algebra of the gauge group. So okay, so this G is the gauge group. So I wonder if there's some connection between.
Yeah, so I think the Atiyah algebroid is central, is also called the gauge, it comments that the gauge is related to gauge, formalization of gauge theories from the algebroid picture.
That's extremely interesting. Maybe you want to give a talk about So it turns out maybe that this example, which seems the most strange, is actually the most central, is actually possibly the motivating example?
I don't know, but it's physically, the most physically related.
Okay, this is extremely interesting. Maybe we can move in this direction. Okay. Let's move on. All right. So this concludes our discussion, our review of Lie algebroids. Are there any questions about this? Actually, any residual questions? Anything? Okay. So now I want to describe the Courant bracket. And so the Courant bracket naturally lives on the double of the extended tangent bundle, which is the double of the tangent bundle, fiber-wise double. So this is the extended. Tangent bundle. And then, as I said in the introduction, then what we'll do is we'll see what we get from, or we'll see what kind of data or information comes out of this definition, and then we'll take that information or data and we'll define, a new construction called a Courant algebroid, which abstracts from the extended tangent bundle with its Courant bracket, with its canonical Courant bracket. Okay, so 2. The Courant bracket.
So Tn, the extended tangent bundle is a real
Yes.
vector bundle.
Yeah. which means that a generalized complex structure on this real tangent bundle is canonically associated with this, recall, like Lagrangian splitting on the complexification of this real tangent bundle. So it seems that in this field of generalized complex geometry, we go back and forth a lot between like real vector spaces and their complexifications. Okay, so the Courant bracket. And I'll just give the definition. So, definition. The Courant bracket on the sections of the extended tangent bubble is defined to be x plus alpha, y plus beta is equal to x, y as vector fields. So just to clarify where everything lives, these are both elements of, or let's see, sections of Tn plus T star m, so that, for example, y is a vector field and beta is a one form on M. Okay, so the Courant bracket on the vector field components is just the standard Lie bracket, and then we add the Lie derivative in the direction of x of beta, and we subtract the Lie derivative of along y of alpha, and then we have this additional term minus 1/2 the exterior derivative of the interior product of x with beta minus the interior product of y with alpha. Okay, so this is the definition of the Courant bracket. In my mind, being also new to this is almost maximally opaque as far as the definition goes. There is opaque, opposite of clear.
Can you please repeat what is alpha and beta?
Alpha is a one form. Let's see, I wrote it down here. So x, y are vector fields, alpha and beta are one forms on M. Is this, so on one form, so this is sections over M of the first, or okay, no, these are sections over M of the dual bundle to Tm. Is this familiar? Have you seen this before?
Yes.
Okay, yeah. Then the sections of the extended tangent bundle are precisely the sections of the tangent bundle plus sections of the cotangent bundle. Okay, so in my mind, this part of the Courant bracket is intelligible, and this part is deeply mysterious. So I think what's going on here is, well, x and y represent directions on M. And the Lie bracket of x and y is the instantaneous rate of change of y along x. So it's the derivative of y in the direction along x, scaled or proportional to the magnitude of x in those directions. Likewise, so actually we could even write this as the Lie derivative of x, along x of y. Likewise, that's the same thing that's going on here. X is a direction, or it just includes magnitude and direction, and we're taking, we're measuring the instantaneous rate of change of beta along x. So we could, in fact, write these first two terms as, okay, I don't want to get too messy, but we could write it as Lx of y, applied to y plus beta. And then this component here is negative the instantaneous rate of change of alpha along the direction y, or in the direction of y. So that's, I think, that this feels familiar. We're measuring an instantaneous rate of change along a direction of magnitude. However, and we can be comfortable with the sign because I think it's easy to see that the Courant bracket is antisymmetric. So this ensures antisymmetry, and maybe there are other ways to see why this might be natural. However, this last term here, for me, I don't have a way of thinking about it. There are some things maybe to notice about it that might make it more maybe more plausible that we could see something here. This term in brackets is the, let's see, this is the canonical antisymmetric bilinear form on the extended tangent bundle of M. So that's x plus alpha, y plus beta. But now we're not adding the cross terms, we're subtracting the cross terms. So I'm going to put a negative sign here. And that 1/2 is part of this, should be understood as part of this canonical antisymmetric bilinear form along the fibers of the extended tangent bundle. But why this arises here, like why we should expect it to arise, I don't have an intuition about that. And I did a Google search and nothing showed up. But I think it will be good to think about and maybe sort of meditate on something. Okay, so here is the Courant bracket. At least the definition is straightforward. Are there any questions about the definition?
Why is that canonical bilinear form?
What is it, or why is it canonical?
Firstly, what is it?
What is it? Okay. So we have a real vector space V, right? We have the double of V. Let's define the double of V to be V direct sum V star. The canonical bilinear form, the canonical antisymmetric bilinear form on the double is given by V plus, I think I used alpha before, or did I?
Yes, you used alpha.
I used alpha, okay. V plus alpha, V prime plus alpha prime is going to be, let's see, alpha prime V minus alpha V prime. So this is the definition.
minus?
Yes.
Ah.
So before we were using the canonical symmetric bilinear form on the double. So let's do plus minus, plus minus. So on the double of V, there's a canonical there's a canonical symmetric bilinear form, and there's also a canonical antisymmetric bilinear form.
And how is this related to the last term?
Because the interior product of a vector field with a one form is just the application of, so the one form here is living in T star M. X is living in Tm. So we could write this as beta of x minus alpha of y, like that. Is that okay?
Okay, but there also difference. We write d of this and
Yeah. To write out the full term, then it's the exterior derivative of this.
okay.
Let's see. So how about I'll write it here. This whole term here is d of x plus alpha y plus beta minus.
Okay.
So I think it's significant. I think I have seen that it will turn out to be significant that this term is exact. That is, that it's the exterior derivative of something. Okay, so very concrete. This is a very concrete definition. Now I want to give some observations, to state some observations about the Courant bracket. I'll just erase this. Or actually, let's take a short break so that the boards, so I can wipe the boards down and dry. What?
So this is the most symmetric, meaningful thing I found.
Oh, that's nice.
Which looks like the vector
Is this correct? Yeah. I'm. Should we? But there's there's a 1/2 here. There's 1/2.
Yes.
Okay. Yeah, and maybe if we even move all the 1/2s to the front and then. Okay, this is a better conceptual definition. This is so this is saying that it's the rate of change along the direction encoded in the first bracket minus the rate of change of the other term, the first term along the direction y encoded in the second part, minus the exterior. There should be an exterior derivative here of the canonical antisymmetric bracket. Oh, this is what. Yeah. So minus the exterior derivative of the canonical antisymmetric bracket on the extended tangent bundle applied to alpha and beta and xy. So, okay.
There should be derivative.
There is an exterior derivative here. It's just that the chalk right here is really wet, and so it crumbles when we write. Right. I think it's
oh yeah, I made a mistake, right?
with
It's not the last parenthesis,
Yeah.
and even with the last term is iota y d alpha.
Beta on x minus alpha on.
Oh, so yeah, so actually
Oh,
I
It's,
made a
it's,
mistake.
it's the flip terms.
Yeah, it's a flip, but
But
actually
you use the flip terms.
it's, let me.
Do you want to post this to the Telegram chat, or do you?
Yeah, I'm just writing it because I made a. So it's iota y, iota x, beta. So I thought it was giving the term I had written, but it's not.
Oh,
Yeah, so it's not the
okay. So this is a two form then.
right. Yes. So it doesn't give the term I had given, but it's not.
It's nice, but now I think now it's not clear that this is exact.
Yeah.
Okay, well it's an alternative expression.
Right, and it's obscure. It's not. we don't
It's
see-
true at least. Well,
Yeah.
Maybe I should have kept this up, but. Okay, I'm actually gonna just write down the definition of the bracket. Each. Okay, so I'm just putting this up here for reference. Right, so now I want to make some observations, I think 2 observations, or state 2 facts about the Courant bracket on the extended tangent bundle. First, so observation. The projection, so here pi is the, let's see, is the canonical projection from the extended tangent bundle to the tangent bundle, and we might think, oh, maybe this is an anchor map, maybe the Courant bracket is a Lie bracket, and maybe we are in the setting of Lie algebroids, but we'll see it's not true. So observation, pi, so the projection applied to xy, or the Courant bracket of x and y. Just to emphasize that I mean the Courant bracket here, I'm going to write C infinity Tm plus T star m is equal to right here, the Lie bracket of pi x, pi y. So pi is a fiber map. Here I'm applying pi to every value of x. So to the values of x at every fiber of the extended tangent bundle and pushing them down to the tangent bundle to obtain a vector field on M, and then here I'm taking their Lie bracket. This is the first observation.
So x and y in the first line are vector fields on M or already.
Yeah, they're vector fields on M,
Okay.
but here I'm applying the Courant bracket,
Right.
and here I have the Lie bracket.
But so in the Lie bracket you could write x and y without instead of pi x or pi y.
That's true.
Right?
Yeah.
Okay.
So I guess maybe this is super formal.
Okay, no, it's
yeah.
fine, it's fine.
I'm gonna.
Just
You're right. I'm gonna write it this way. Courant is equal to xy canonical Lie bracket. Okay. The Courant bracket of x and y is equal to the Lie bracket, or the canonical Lie bracket of x and y. That's better. Okay. This is clever. So the upshot of this is just that the Courant bracket extends the canonical Lie bracket on the sections, or the canonical Lie bracket on the vector fields on M. The second fact that I want to state is that the Courant bracket is not Jacobi, or it does not satisfy the Jacobi property. Therefore, the Courant bracket is not a Lie bracket. And thus, the extended tangent bundle with the canonical projection pi here to the tangent component, equipped with the Courant bracket, is not a Lie algebroid. Okay, so this is the first important fact. The extended tangent bundle with a Courant bracket is not a Lie algebroid. But maybe unsurprisingly, we're going to see that it's a Courant algebroid. Yeah.
Why the first is true?
Up there?
Yes.
Well, so if alpha and beta are 0, then the Lie derivative of 0 with respect to any vector field is 0 for
Okay.
all other terms vanish. Okay, so I thought maybe there's an easy example. I couldn't find an easy example, but it's a fact. Okay, so we'll see that even though the Courant bracket does not satisfy the Jacobi property, we can still characterize the extent to which it fails to satisfy the Jacobi property, and this, in some sense, will characterize the extent to which the extended tangent bundle is not a Lie algebroid. So this is measuring. So this is going to sort of measure the distance between our Courant algebroids and the algebroids, in some informal sense. Okay. So definition. So we have two definitions here. First definition: the Jacobiator of the Courant bracket is defined to be, or defined by, Jack ABC equals cyclic permutations of terms of nested brackets. Where here A, B, and C are elements of the extended tangent bundle. That is, A, B, and C are all of the form x plus alpha. So in the case where we have a Lie bracket, the Jacobiator is 0. So this Jacobiator is, again, sort of measuring the extent to which our bracket, our Courant bracket in this case, is not Jacobi, or does not satisfy the Jacobi property. We're going to need another definition. So the second definition. The Nijenhuis tensor, I think it is a Norwegian name? Nijenhuis?
Nijenhuis.
Nijenhuis? Nijenhuis.
Yes.
Okay. The Nijenhuis tensor is given by Nij, I won't even try, of ABC is defined to be 1/3 of, the following expression, the canonical bilinear symmetric form on the generalized tangent bundle of M applied to the Courant bracket of AB and C plus cyclic permutations of that.
So the Nij is 9. Is the IJ stands for the second and third letter of the...
That's right. Yeah. Oh, okay. Yeah. So it's like a cyclic average, or an average over this. And then proposition. The Jacobiator of ABC is equal to the exterior derivative, so again we now have something exact, it's equal to the exterior derivative of the Nijenhuis tensor, Nijenhuis?
No, you said it right. Nijenhuis.
Nijenhuis tensor of ABC. So that's interesting. We see that the extent to which the Courant bracket fails to satisfy the Jacobi property is exact. It's given by the exterior derivative of this expression here.
What means these brackets?
Which ones? Here?
In definition of
Yes.
tensor.
This is the canonical bilinear symmetric bracket on the double that we saw in previous lectures. So in terms of what I had erased, this is the plus bracket. So this is defined fiber-wise as the vector, so tangent vector part of the first term combined with or evaluated by the covector part of the second term plus the covector part of the first term applied to or evaluated on the vector part of the second term, and all of that scaled by 1/2. Does that? So this is just the bracket that we saw before. Okay. And for a proof, see Gualtieri or his thesis proposition 3.16. So, I should say that basically everything in this lecture, in this particular lecture, basically everything is following very closely the exposition given in Gualtieri's thesis. Yeah.
One more question. Where does this tangent reach in
Here?
Yeah.
This is a section of the extended tangent bundle.
No, it's not. So it's this is.
So it's an element of.
It's an object. Yesterday was a bracket, and today is a three tensor.
It's an element of
So it's
sections
not,
of Tm plus T star m.
so it doesn't apply to the same.
So you can see that by just noticing that. Okay, so the Courant bracket of C and A here is going to be a section of the extended tangent bundle, right?
Yes.
And then we take fiber-wise, or when we apply the canonical symmetric bilinear form fiber-wise to this section and this section, that gives us another section. And then we just add the similar terms. Great. Let's see what time it is. Okay.
It's just a derivation of it's similar to the first.
So second proposition.
Just a
Yeah.
question. The pairing is
With the 1/2.
with the 1/2?
Yes.
Okay.
Great. So now we're going to, okay, so here we saw how far the Courant bracket is from being a Lie bracket. Now we're going to see how far the Courant bracket fails, or the extent to which the Courant bracket fails to satisfy the Leibniz condition. So now we're going to let f be a smooth function on M. And again, A and B, sections of the extended tangent bundle. Then, the Courant bracket applied to A and FB is equal to okay, I'm just going to write it out and I want to talk about it. F times the Courant bracket of A and B plus the plus pi applied to A times F multiplied by B, so scaling B, and then minus the canonical symmetric bilinear form on the sections, or fiber-wise on the sections of the extended tangent bundle times the exterior derivative of f. So then what I want to say about this is that note that this is the, so this equality of the left-hand side and this bracketed term here is, or it expresses, so without this part, expresses the Leibniz condition. So we see that we almost have a Leibniz condition, but we have, but there's this this extra term here. And again, this extra term now involves exactness. And it's actually not, it's technical, but not, I think, particularly revealing to establish this. So I'm going to state the final proposition, final proposition or property. And that's that the vector field component of A, so again, everything is living in the same space as above, the vector field component of A applied to the symmetric bilinear form, canonical symmetric bilinear form of B and C, and note that this is a function. So this is going to be a function. And also note that this doesn't really have an equivalent in terms of our Lie algebroid formalism. This is something particular to Courant, to our new setting of Courant algebroids, because in the Lie algebra formalism we don't have a we're not given a symmetric bilinear form on the fibers. That's not part of the data that's included with a Lie algebroid. So this is equal to this expression, a canonical symmetric bilinear form applied to the Courant bracket of A and B plus the exterior derivative of the canonical symmetric form applied to A and B, and then C plus B, I'm just going to write it out, AC plus D AC. So if you're like me, this looks very technical. I don't have an account for why we should expect this to be true, but maybe let's, well, okay. Okay, again, if we ignore the exact terms, then it looks like we're applying that it looks like A is acting as like a derivation on this bracket. So this is equal to A applied to B plus A applied to C. Except, right, so that's what we have here, except that we have these new exact terms. Okay. This concludes our introduction to the Courant bracket. Now we're going to take from this discussion the information or the structure encoded in the propositions, and we're going to define a new construction called a Courant algebroid. So this is section 3. Courant algebroids. And this section consists of one definition, but this definition is an impressively long one that will fill this entire board plus this bit that we have here. So definition, and this is going to be phenomenally technical. A Courant algebroid on M consists of so 4 data, 1, a vector bundle, E over M, 2, a non-degenerate symmetric bilinear form, non-degenerate symmetric bilinear form. So angled brackets, this is like our canonical symmetric bilinear form for the sections of the double. On sections of E. So this is given in Gualtieri's thesis. So this is a little bit different, I guess, than precisely what we had before, where the bracket is induced. So where the bracket on sections is induced by a bracket on fibers. I don't know if that's implied in this case or if we don't need that property. But this is how it's given in the definition. 3, a skew symmetric bracket so square brackets on sections of E, smooth sections of E. And finally, 4, an anchor map. Pi from E to the tangent bundle of M. So far, okay, so for the data that's for the data that is involved in the definition of a Courant algebroid, everything here is pretty much, or is very similar to the definition or the construction of a Lie algebroid, except now we have a non-degenerate symmetric bilinear form on the sections of E. That's new. So this is new to our setting, so I'll put a star next to it. And the second thing that's different is that our Lie bracket on the sections is now just a skew symmetric bracket. Okay.
What is skew symmetric?
Oh, it just antisymmetric. So you switch the elements and you pick up a negative sign.
Okay.
And then we have a definition within a definition. The associated differential operator D from is this okay? Yeah. On functions on M, so on smooth functions on M. Is defined so it's defined in the following way. And this is well defined because the brackets are non-degenerate. So df evaluated against A is equal to 1/2 pi of A times f. So we've now defined a new differential operator on functions on M. So these functions a priori have nothing to do with the Courant algebroid. So this is kind of parenthetical. So I'm going to put it in large brackets.
So it takes values in
Smooth functions.
smooth functions.
This is a vector field. It's a vector field applied to the function f.
Yes, but on the left-hand side, df bracket.
Oh. Hang on.
So I think it's
Aha, we
in the
want,
section.
yeah, we want sections. Thank you. So then, what is this? Can we take some things?
No, I think now it's fine because on the left hand side this is the pairing.
Oh,
On the right
yeah.
hand side it's.
So we want it from smooth functions
Oh, yeah.
to.
Yeah. I think that's it.
Have you seen this before? Is this
Yeah,
seems like
I
a
think
strange?
I mean it's standard. It's in the lecture notes of this is the
Okay.
algorithm.
Okay.
The White but
Okay, this is a new, so it's a differential operator from functions to sections.
yes.
Okay,
Right. Yeah. It's
let's see where it takes us. All right.
yeah, that's cool.
Okay. Subject to the following compatibility conditions. So such that. Now we're jumping back to the original definition. We're going to use this differential operator such that 5 compatibility conditions are satisfied. So 1, pi applied to AB, or the anchor map applied to the Courant bracket, or the bracket of A and B is equal to A, pi B, in terms of vector fields. So this condition is pretty straightforward. This is just saying that the anchor map induces a bracket homomorphism on sections. Oh, yeah.
Can I ask,
Yeah.
in the definition of Courant algebra, the second, yes.
Yeah.
The bilinear column map pair of sections to function.
Yes. Yeah.
Oh yes. Yeah.
Yeah. So a form normally takes. I think a form. It's implied that that the term form would be real valued or complex valued. I think. All right. So first we have a bracket homomorphism condition. This one sort of makes sense. Then we want the Jacobiator of ABC. I'm not going to write where everything lives. It lives. All these things live in the same place where they did before. Is equal to the our associated differential operator applied to the Nyquist tensor of ABC. Can we fit everything? Okay. Third, we almost have a Leibniz property. So the bracket, the schizometric bracket of AFB is equal to a Leibniz part plus a exact part. So FAB plus pi A F B minus AB df. Oh, so now exactness is like this script D exactness. Fourth, df dg, script df, script dg vanishes for all, so here I will write where they live, for all f and g, smooth functions on M. So this is also characterized in Gualtieri's thesis as the fact that the induced map on sections by the anchor map vanishes on exact terms, on script D exact terms. And finally, we have that this sort of skew or this like derivation up to exact terms property. So pi A applied to BC is equal to AB plus script D AB C plus B AC plus D AC. And this is the definition, and this is section 3. So I think what we'll do next time is to try to get some intuition about some of the things that we described and introduced today. I think for me this is an unusually involved construction, and I think it's definitely worth trying to spend some time to understand. Yes.
So there is an alternative form definition,
okay.
which actually came afterwards, and it's much more transparent.
Okay.
Because everything is in terms of derivations of so.
Can you share it on the Telegram chat?
Yes.
And then
yes. Okay.
And then we can maybe next time we can compare the definitions, and we can just as a process of understanding what's going on underneath.
Right. Yeah,
underneath a lot of this. Great. Any questions, comments, concerns?
Our extended tangent bundle is an example of Courant algebra.
Yes, yeah. Well, at least in the development that we have here, it's the motivating example of a Courant algebroid. A Courant algebroid is basically something that looks like the extended tangent bundle with its canonical Courant bracket. All right, well, if there are no more questions, then let's reconvene next week.